Hi, my name is Christina Kwok from Chem 111, and we're going to be solving a gas problem today. The problem reads, ammonia is added to an evacuated 6-liter flask to a pressure of 8.00 atmospheric pressure and a temperature of 25 degrees Celsius. Carbon dioxide is added to the ammonia to give a total pressure of 18.00 atmospheric pressure. The flask is then heated to 110 degrees Celsius. Calculate the total pressure in the flask at the new temperature when the reaction is complete, assuming 100% yield. So we know that we're assuming there's 100% yield. So if you look at the chemical equation, we know that one of the reactants will be completely used up and will not be calculated as part of the total pressure and once the reaction is complete. So if you look at the visual here, we have NH3 and then the carbon dioxide was added and it's in the 6-liter flask. And we're going to first try and figure out how many moles of each of the reactants are present by using the ideal gas law. And PV equals nRT is the ideal gas law, but we're going to set the equation equal to N to figure out how many moles of each of the reactants there are. Okay, so before the reaction is taking place, we want to figure out how many moles of each reactants are present. So as you can see, the moles of NH3, we can figure that out by using the partial pressure of ammonia, as well as the volume that it wasn't contained in, and over the R value, the constant, as well as the temperature, which was at 25 degrees. If you plug in the numbers, the partial pressure of ammonia was 8.00 atmospheric pressure in a 6-liter flask over 0.0821 liters times atmosphere over mole times Kelvin for the R constant, and you multiply that by the temperature, 25 degrees, which is equivalent to 298.15 Kelvin. That gives us 1.96 moles of NH3 before the reaction takes place. For the second one, to figure out the moles of carbon dioxide present before the reaction, we have to first figure out what is the partial pressure of carbon dioxide. We know that the total pressure in the flask when the carbon dioxide was added was 18, but in order to figure out exactly how much partial pressure of the carbon dioxide is contributed into that flask, we have to subtract it from 8.00 atmospheric pressure, which is the partial pressure of the ammonia. If you do that, we get 10.00 atmospheric pressure of carbon dioxide. Using that information, we plug it into the equation again, and we do 10.00 atmospheric pressure times 6-liter flask over 0.0821 constant for the R times 298.15, we get 2.45 moles of carbon dioxide, and this is the amount that we're starting with. So we have 2.45 moles of carbon dioxide initially and 1.96 moles of NH3 present initially. After the reaction has taken place, we want to figure out which of the reactants is a limiting agent. So what is the maximum amount of water vapor that can be formed? In order to do that, we're going to use the moles we found of ammonia as well as the moles of carbon dioxide that was present initially. So if you look at the chemical equation, we know that we start off with 1.96 moles of ammonia, but for every 2 moles of NH3, we form 1 mole of H2O gas, and that equals to 0.980 moles of water vapor gas formed. And we compare it to the carbon dioxide. We start off with 2.45 moles of carbon dioxide, and for every 1 mole of carbon dioxide, we form 1 mole of water vapor, and that gives us 2.45 moles of water vapor. From here, we know that the ammonia is the limiting reagent because it gave us the lowest number of water vapor formed, and that also means that when we are calculating for the total pressure, the partial pressure of NH3 will no longer be there because it has been all used up. So now we have to figure out how much of the carbon dioxide reacted with the ammonia. In order to do that, we use the same mole ratio again. So we start off with 1.96 moles of ammonia. For every 2 moles of ammonia, we used 1 mole of carbon dioxide. That gave us 0.980 moles of carbon dioxide. That is the amount that we used for the reaction. To find out how much of the carbon dioxide gas is remaining after the reaction, we just subtract it from the initial moles of carbon dioxide we started. So we do 2.45 moles of carbon dioxide minus 0.980 moles of carbon dioxide that was used, and that gives us a remaining of 1.47 moles of carbon dioxide. We can now use these numbers, the remaining of carbon dioxide as well as the the moles of water vapor gas that was formed and plug it into our ideal gas law to figure out what is the total pressure present in the flask after the reaction at 110 degrees. So we're using the equation again, PV equals nRT. Now we're solving for the total pressure, so we're going to set the equation equal to P. When we do that, P will equal nRT over V. So we just plug in the numbers. So we know that the moles are going to be a combined moles of the remaining carbon dioxide gas as well as the mole of water vapor that was formed. So it's 0.908 plus 1.47 moles. Multiply that by the R constant, which is 0.0821 liters times atmosphere over mole times Kelvin, times the 110 degrees Celsius, which is converted to Kelvin at 383.15 Kelvin. And we divide all of this over 6 liters flask, and that gives a total pressure of 12.8 atmospheric pressure present in the flask after the reaction is complete.